So in our previous topics, we focused on the concept of heat, right? We really addressed this idea of what is heat, right? How do we transfer heat? How do we measure the amount of heat transferred? And we've done that by thinking about this idea of energy change, right? If we look at energy change, right, we're going to think about it's the change in energy undergone for a reaction or a process. Well, so far we've only said, well, the only way that energy change happens is if we produce heat or absorb heat. But when a reaction happens, can something else happen? Can we use that energy to do something else? Well, hopefully, otherwise then we're stuck with just being able to warm things up or cool things down, right, from reactions. So we're also going to talk about this other idea of work, okay? So these two values are energy values, are ways that we can look at a change in energy, okay? So what we'll see is that change in energy for a reaction is going to be equal to the amount of heat that it absorbs or releases, plus the amount of work that it does or has done on it, okay? There's multiple different ways we can talk about work, right? I think we've really addressed this idea of heat. We can measure it. We can look at it being measured from changes of temperature, but we haven't really talked about this idea of work, okay? And where does this work come from? How do we talk about it? Now, primarily the work that we're going to focus on is this idea of expansion work, okay? So expansion work is kind of first discussed with this idea of we have work that's being done by or on a system based upon a change in volume, okay? So this is expansion work. So we can think about a reaction expanding or contracting, right? We can think about this idea. We have a container here, and we have maybe a movable piston sitting on top of that. So sitting on top of this is a constant pressure. So when we're talking about expansion work, it's got to have a constant pressure sitting on it, right? This is this P value here. Well, we can go ahead and see that we can have our volume increase. Okay, and we're going to talk about what does that mean. And we can also have our volume decrease. And what does that mean with regards to work? Okay, so if we look at our volume increasing, we think, well, inside of here is our system, and outside of that is our surroundings. And remember, we always talk about heat and work as the system releasing heat or absorbing heat, the system doing work, or having work being done on it, okay? Well, you think about the system. In order for the system to increase its volume, it's going to have to push up and push out on that pressure sitting on it, okay? So if we increase the volume, what we're going to see is that our system does work, okay? So if our system's doing work, it's going to cause it to expand, okay? So the opposite would be true if we have our system and it's being pushed down. Well, something's doing work on our system and pushing it down and compressing it. And so we see here is work done on the system. Okay, so the system is doing work here when it's expanding, work's being done on the system when it's contracting. Now, why do we necessarily care about this? We would see this as quite important when we talk about gas reactions, where we have something expanding because we're producing gas or contracting because we're decreasing the amount of gas, okay? So we're talking about this idea of expansion work. If our system does work, well, if you're exerting energy to do work, you're having to give that energy away, okay? So if our system does work, we can think about that as being a negative value, right? Our system is losing energy, okay? If our work's being done on our system, it's gaining energy. Somebody's doing work to it, right? First law of thermodynamics, we can't gain or lose energy. And so then that would be a positive value, right? It's absorbing energy, okay? So again, now we have the ability to have endothermic, exothermic reactions, positive and negative energy changes, or work being done on or by the system, positive, negative work energy changes, okay? The final thing I want to mention is that, well, this seems like something that's kind of arbitrary. Can we actually measure this looking at a reaction? Yes, we can also redefine this as being work is equal to negative change in moles of gas times R times T. Okay, so R is the gas constant, right? Okay, so we have our gas constant, and then T is our temperature in Kelvin. Okay, so remember our gas constant has units of Kelvin as the temperature. The final thing that we look at, well, what is this change in moles of gas? Okay, so the change in moles of gas is the difference in the number of moles of gas of our products, so how many we end up as a product, minus the number of moles of gas as our reactants. Okay, so we undergo a reaction and we see we can get a change in the number of moles of gas that we produce or at the end. Okay, so we go ahead and maybe we want to look at an example of this. So let's go ahead and bring that right back up here. And so we see, well, maybe we go back to our reaction we looked at last time. So hydrogen reacting with oxygen to give us water. We go ahead and we balance this. Okay, so if we see, we start with here 3 moles of gas as a reactant. We end up with 2 moles of gas as a product. Okay, and so we would say, well, if we're sitting at constant pressure, it's going to contract, right? We have start with a large number of moles of gas, end up with a smaller number of moles of gas. It's going to contract. Well, when it does that, work's going to be done on it. Well, we can go ahead and we see, we could calculate that, right? The change in the number of moles of gas is going to be 2 minus 3 or -1. Okay, we could go backtrack and we'd see, well, that's going to end up with us having a positive work value, right? Negative, negative, R and T are both positive. And so here, we're going to have work is going to be a positive value. Okay, so hopefully this gives us a good introduction into this idea of energy change, how that relates to work and heat. And then in class, we're going to talk more about this idea of calculating how much work is actually done by or on a system, as well as predicting that based upon reactions. So I hope to see you then.